Let us now see how control NOT gate generates quantum entanglement. Let's analyze this circuit. We have two qubits. They start, both of them are initially prepared in state 0. So let's step through the circuit and see what we get at the output. So at the very beginning we have state 0, 0. Then the first qubit is modified by the Hadamard gate. So the first qubit goes into state 1 over square root of 2, 0 plus 1. And the second qubit stays in state 0. So we can write this state as 1 over square root of 2. So I'm going to expand it. So I have state 0, 0 plus 1, 0. So that's after the Hadamard gate. Now it's time for the control NOT. You've been waiting for this moment, right? C0 gate. So let's look what is going on here. So this is my control qubit, this is my target qubit. When the control is in state 0, nothing happens to the target. When the control is in state 1, we flip the target, right? So we have the state 1 over square root of 2. Now this one stay as it is, and this one, in this particular case, the control is in 1, we flip the target, so we have state 1, 1. Now if you look at this, this state, so it is a superposition of two configurations of two qubits. Configuration 0, 0 appears with probability amplitude 1 over square root of 2, and configuration 1, 1 appears with probability amplitude 1 over square root of 2. Now, when I ask you this question, can you attribute any particular state to the first qubit or to the second qubit? Then when you look at this expression and try to think a little bit about it, then you realize that it's not possible. For example, in contrast, if I were to write this state 0, 0 plus 0, 1, and I ask you the same question, then you would say, well, yes, you can do something about this state here, because I can look at it and I can see that I can factor out the state of the first qubit. So that state is equivalent to the following state, 1 over square root of 2, 0 plus 1. So you see, so this one I can write as a tensor product of the state, a well-defined state of the first qubit, which is 0 in this case, and the second qubit is in an equally weighted superposition of 0 plus 1. When you try to do it with this state, no luck. Just try as hard as you want. You will not be able to write this particular state as a state pertaining to the first qubit tensor product, the state pertaining to the second qubit. So this state is entangled, this one is separable. Another thing you can do is you can try different inputs for this circuit here. So we can see that input 0, 0 generated, so this is the bit value of the control, the bit value of the target, generated the state 1 over square root of 2, 0, 0 plus 1, 1. Now, if you take input 0, 1, then you will generate the state 1 over square root of 2, 0, 1 plus 1, 0. And if you take 1, 0, so this one will give me, there will be 1 over square root of 2 everywhere, right? So it's normalized state. And in this case, I'll get 0, 0 minus 1, 1. And the last case gives me 0, 1 minus 1, 0. So you see, input 0, 0 generates this state, input 0, 1 generates state equally weighted superposition of 0, 1 plus 1, 0. Input 1, 0 generates equally weighted superposition, but this time I have here state 0, 0 appearing with probability amplitude 1 over square root of 2, and state 1, 1 appearing with a probability amplitude minus square root of 2. And finally, the input 1, 1 generates the state 1 over square root of 2, 0, 1 minus 1, 0. Those states, the states here, are rather special. They're maximally entangled state, whatever maximally means at this point. But think about it this way: they're equally weighted superpositions of those basis states, and they are known as the Bell states for 2 qubits. Quite often we will mostly use this one and call it omega state, because we can play all kind of nice tricks with this particular state. But every now and then we will use this one, and you can see we started with computational bases 0, 0, 0, 1, 1, 0, 1, 1. So 4 bases in the tensor product of this tensor product Hilbert space pertaining to 2 qubit. And we applied a unitary operation, which is constructed as the Hadamard and control NOT gate. So that rotated the 4 basis vectors into something that we call the Bell basis. So the Bell basis is another set of 4 mutually orthogonal. So we are switching from one orthonormal basis to another orthonormal basis here. But this basis is kind of interesting because it's composed of entangled states. And as you can see, in some cases it's actually more convenient to switch into that kind of basis.